So I'm Richard Webb, and you are all the names that I just said. Here's the syllabus. I pricing the names, you know. Juliet. Alex. Mr. Rossi. What's his first name?
Huh? Clayton.
Clayton, right? It's not hard to pronounce it, remember.
It's a nice English name.
And okay, so that's the syllabus. I'm not actually going to be looking at the syllabus, but I'm going to be going over it here. Welcome to astronomy class. What we do in astronomy class, hey, check this out. I can use this little thing to move forward. Is, of course, study the sky, but much more than that. We want to understand what's going on out there. Our textbook is the first brightest spot of this whole class. It's a new textbook from OpenStax, and it's free, as in no money spent. Also, if you look in there, you'll find my name. I was one of the reviewers of the textbook. So there's the link to take you to it. You can click the link in the syllabus, whatever you want. Set up a bookmark on the computer you use regularly. If you want to have a hardbound copy of it, you can purchase one for a little under $50. But if you are happy with the free book, then you have it free. Class times, 2 o'clock, Monday, Wednesday, Friday, right here. Laboratory, 8 o'clock to 11 p.m. On Tuesdays, meet here. If the weather is good, we'll be going out, we'll be walking out. We'll get our exercise. Or you can drive your car. Because I've become married, I now drive. Before that, I walked. We're going to walk out to Holmes Lake, which is conveniently right next to my house, so I won't be returning. So don't leave anything in the classroom. We go out there because it's darker. My first year, I tried to do lab here on campus, and you just can't see the sky. Also, for the first month or two, I will actually be lecturing for the first hour of lab because you really can't see much in the sky until an hour after sundown. And right now, sundown is occurring basically at the same time lab starts. So you don't really see anything. If we went out there, right, start a lab, it'd just be, okay, well, there's the moon. Okay, so those are our times. My objectives, and this may look familiar to a couple of you because my objectives are similar. The scientific method. A lot of people are in a class like this because of education reasons. And in fact, you said, you're in here because of being science education. And one of the things that is very important to me is that the people who are teaching our youngsters science in grade school know what science actually is. Yeah, because a lot of people just think science is, you did this experiment, the end. And they don't understand the process. What makes something a science is following a specific methodology called the scientific method. And so that scientific method is like the most important thing I want students to get out of this class is understanding the scientific method, how science operates. So I'm going to a little bit go through the scientific method. On the first exam in this class, you are going to have a question that says to list the 4 steps of the scientific model or scientific method as I laid out here. And so you basically have to memorize those 4 steps. And then it's going to give you an observation, and you're going to have to apply the scientific method to that observation. And so you're going to have it memorized, now it'll be 4 points. And then you'll have to apply it, that's another 4 points. So that'll be a total of 8 points on a test that's worth about 50 points. Well, it's probably 50 points plus 8, so about 58 points. Well, that's a really big fraction of the score of the test, right? So it's really important to me. The final exam will have the same question but a different observation. So it's going to be tested on 2 different tests. You know exactly what the question is, except you don't know what the observation is, because it's really that important to me. Then I really want you to name the planets in the solar system. How many people already know the planets in the solar system? Okay, so have pretty much everybody surreptitiously raise their hand. So that part's probably going to go easy. I was on an astronomy news group once, and somebody's asking, what's the best mnemonic you know for naming the planets? There's my very earnest mother just served us. My students decided when Pluto got kicked out that they changed the last word to nachos. And somebody said, well, my favorite mnemonic has always been Mercury, Venus, Earth, Mars, Jupiter, Saturn. Anyway, but if you already know it, that's great. Understand the life cycle of a star. The life cycle of a star is going from before there was a star, when it was a twinkle in the eye of the universe, to when it dies and becomes the bones of a dead star. So we want to understand that process for stars being born, living, and dying. And of course, they don't really live, they're not biological, we anthropomorphize them. Being able to impress your dates. Okay, that's really important. You want to be able to go out there with your honey and say, oh yeah, there's, Sagittarius, he's the archer, but it looks like a teapot to me. And if you just go out where the tea would be pouring, that's where the center of the Milky Way galaxy is. And then your date, if they're a normal human being, she goes, oh, you win, right? That's a big goal right there. And that's what we'll work on in lab. And then know the benefits of science to humanity. Astronomy, oftentimes we're like, what is the purpose of astronomy research? Why does NASA spend so much money on doing their research? And of course, those of you who were in class this morning, when I pointed out they lost millions of dollars by having the wrong units calculation. Well, some of the benefits that NASA will tell you is all the things that are developed in doing the research to try to get these things going. A lot of basic fundamental research is funded by NASA, also by the military, that comes out to be other things. Things like our microwave communications that we use in our cell phones is the result of military research. So there's those kinds of benefits, but I just want you to have some appreciation for what I forgot. I don't have to come back here. This is a new thing for me, being able to tap the end of my pen. Academic integrity, don't cheat. I don't expect you to cheat, by the way, but I always have to go over this. Don't copy somebody's work. Don't give your work to somebody else to copy. As you can see, I just copied this slide from one presentation to another. That's okay. Actually, when we were talking about plagiarism, Tanya Cochran said there is such a thing as self-plagiarism. If you copy something you wrote, you have to reference. I actually wrote it here first. So I'm telling you, I wrote it for my physics class and copied it to here. But oftentimes people think, I went to a website, all of your homework problems are coming from the textbook. And those textbook problems, almost certainly people have put answers out on the internet. Well, if you just go and search on the internet, find somebody's answer and paste it in, that is cheating, right? That's not answering yourself, that's letting someone else answer it for you. And Chegg is just one of those big cheating websites, so I always use it as the example. Classroom decorum. With this many students, it's pretty clear I'll be able to see who's texting and who's not. Come to class, be on time, pay attention, don't be doing other stuff in class, and don't walk in and out. If you have to go to the bathroom, you have to go to the bathroom, right? I'm not going to say make a mess, right? But you shouldn't be going in and out excessively. And certainly if you bring your cell phone to class, which I did, you should have the ringer off, which I did. Okay, how is your grade determined? My goal, I have never reached whatever the proper form of the word reach is in this case. I have never met this goal, but my goal is to have one quiz a week, excluding weeks when we have a test. If I get over 7 quizzes, I will change it from 1 drop quiz to 2 drop quizzes. But for me to get over 7 quizzes is hard because I always forget to give them. Now, Gene's all down with that. The quizzes will be given at the beginning of class and in the first 5 minutes. So if you're more than 5 minutes late on a day there's a quiz, you're just going to get a 0 on that quiz. It's not announced what days they're going to be. The reason for that is so that you will be, as they say, separatus, always prepared. Funny joke I read in Reader's Digest. A guy in the Marines wanted to have the Marine hymn played at his wedding. The Marine hymn being Semper Fidelis, always true. And instead they played, I forget if it's the Army or whatever, they played Semper Paratus, always prepared. It's on a whole different context. Anyway, so quizzes will be 10% of your grade, not announced, beginning of class. My goal is 1 per week. You get 1 drop, and if I get to more than 7, I'll give you a 2nd drop. Homework, there'll be homework due every week. The first homework assignment, it says there's a homework assignment due Wednesday. There probably will be, I haven't made it yet. So that's another thing for me to do when class gets out today. The first homework assignment will obviously be pretty slim assignment. But the homework assignments, you can either do them on paper and give them to me by 5 p.m. on Wednesday, or you can turn it in as a PDF file on Moodle anytime before midnight. So you have more time than just 5 p.m. The reason for the 5 p.m. is because I want to go home. But you can still turn it on the computer and up until midnight. And I prefer, obviously, that you turn it on the computer because what I'm going to do is download the files, upload them to another website, grade them there, download them back, upload them to Moodle. Question, Eli?
The homeworks will be on Moodle.
Yes. The homeworks will all be on Moodle because it turns out there's no question numbers in the textbook questions. And so I can't really say, chapter 1, question 17, if they're just all listed without numbers. You're going to have to go 1, 2, 3. I sure hope he counted the same way I did. So they'll all just be on Moodle. Okay, laboratory. Laboratory, like I said, every Tuesday night. Your grade in laboratory will be largely based on attendance. If you come on time and you stay throughout lab, you're generally going to get full credit for that night's lab. When the weather is inclement, then we will do other types of activities where there will be alternate scoring methods. So it depends on the weather a lot. Sometimes, I've had years when we've only had like 2 nights where it was clear. God controls these, not me. And in that case, then we got to do a lot of activities. And the activities, like I said, are graded based on the activity. Laboratory, also there is a lab final. The lab final, when I say this, when I first read it, okay, so I picked this up from when I first taught astronomy. I took a teacher who taught the year before me, and here was his lab final. I was like, wow, that seems like a lot you're asking. And then after teaching class, I was like, wow, after like the 2nd or 3rd lab, everybody could do the lab final, or they should be able to. So the lab final is something that you cannot take until the time changes. The reason I make it you can't take until the time changes is because I have a few things that I want you to point out that you can't see in the sky until later, either later tonight. I'm sure we could do it at 4 a.m. this week, but I am not going to be up at 4 a.m. this week, just hot tip. So when the time changes, we'll be able to see these things in the evening. But you'll have to point out 15 constellations or asterisms, pointing out where they are in the sky, giving some description of it. So you can't just memorize, okay, so I know that there's the Big Dipper. You have to actually be able to point them out. And then you have to be able to point out and name 10 separate stars, which seems really hard, but it turns out to be really easy. And then you have to point out 5 specific things. There's the brightest star in the sky, the equinoctial the Andromeda Galaxy, the Pleiades, and there's one more. Oh, and the red giant. You can't double dip, so you can't use the brightest star in the sky as both a star and the brightest star in the sky. Likewise, you can't use a red giant as both a star and the red giant. Pretty sure I missed one thing there, but 15, 5, no, that was it. That's what the lab final is. And so that's something you can't do until the time changes. Now, with only 8 students, or 7 as we have in attendance today, 9 if everyone I approved the class were to show up, we'll probably be able to finish this quickly. But I always have a policy that after Thanksgiving break, Well, wow, this year I think that's only one. Anyway, after Thanksgiving break, you don't have to come to lab if you completed the lab final. Because all I'm going to be doing is finishing the lab final with those who haven't completed. Now, if you had to miss a lab, and it was just an observational lab and not an activity lab, the way that you can make up those labs is to come to have already finished your lab final and then come on one of those last 2 days and point stuff out to other classmates who haven't finished. So that's how you can make up a lab if you have to miss one, right? If you're sick, you can't come, right? And that's how you make it up. Okay, midterm exams. I think we have 3 midterm exams and 1 final exam. The midterm exams, 35% divided by 3 makes each one 11 2/3%. And then the final exam is 15% of your final grade. It's specified in the syllabus when each of these are, so you can see and prepare. Attendance is a little special thing. It's my extra credit thing for people who are showing the effort by coming to class and paying attention. So I read somewhere Union College had a policy that you could miss 1 lecture per number of lectures you have in a week in the class. So we have 3 lectures a week in class, so you can miss 3 lectures and still, as far as I'm concerned, perfect attendance. And so that's what I grade this on. I grade if you show up on time, which you all did today, except for Leslie. If you show up on time, you get 3 points. If you're here, but you are 5 minutes or less late, you get 2 points. If you're more than 5 minutes late, or if you're on your phone texting all day, then you get 1 point. And if you don't show up, I assume it's excused the first 3 times you don't show up. After that, then it's just an absence.
I am so sorry.
Look who showed up, everyone. It's the L person.
No.
So, given that the L person showed up, and I always write this down, you probably notice, when somebody comes in, I write down how much they were late. So this says 18 next to her name. How many points does she get for today? 1. We just got through this. Nice start, Leslie. See, it started with me taking record, and I just counted you as present by habit. And the problem is I had 8 people, and there were only 7 here. Yeah. That's how they all knew you weren't here. I'm sure you have a reasonable excuse.
Yes, I do.
Okay. So if you miss 9 points or less, you get that 2% bonus. If you miss more than 9 points, you don't. If you miss more than 18 points, then it starts going the other direction. Don't miss more than 18 points, okay? You guys don't seem as excited about that. The exams will all be true and false or multiple choice questions except for 1. 1 question will be something more involved, like the one I was telling you about with the scientific method. There's a lot of drawing there. We very well could have a problem on one of the tests later on where you have to draw an HR diagram. You have to draw a graph and know where the things are on that graph. So there will be 1 special problem that is graded differently, but all but that one, true, false, multiple choice. And of course, the special problem always has more points than 1 point. The true, false, multiple choice are all equally weighted as 1 point. And like on the first exam, that special problem is 8 points. So it's worth 8 normal questions. All right. And finally, the slide that I lifted from Dr. Dickerson this morning, just to make sure that we're all clear on the expectations. I expect you to read the material before you come to class. That is, you can look in the syllabus, and the back page of the syllabus lists our schedule. And you can see that for today's class, it's chapter 1, sections 1 through 3. For tomorrow's class, chapter 2, sections 1 through 3. Tomorrow, excuse me. Actually, it is tomorrow. Because tomorrow night for lab, I'll be lecturing. And then if it's clear, we'll be going out. If it's not clear, we'll be doing alternate activity number 1. So make sure that you do read that. So when I'm talking about these things, you have an idea of what I'm talking about. While I'm looking at this, you can see that our goal for tomorrow night will be basic stargazing. We'll basically go out, basic. Learn how to identify something to get you oriented and how to find constellations and that kind of thing. And you can see the homework there, due Wednesday, homework 01. And so you've got the whole schedule here. No confusion there, I hope. If you have a relevant question, please do ask it. Leslie?
You probably already talked about this, but how do we do the homework?
Okay. The homework, you can do it on paper or you can turn it in on Moodle. The questions will be posted on Moodle. The questions from the textbook.
It's like physical science. It's like physical science.
Yeah.
Okay.
Okay, yeah, so I can stop.
Okay.
Exactly. So you got by 5 p.m. on paper or by, actually, the new version of Moodle, I can do it at 11:59 instead of 11:55. It gives you 4 extra minutes. So ask questions if they're relevant, and that was relevant. And remember that learning is the most important thing, not the grade. Grades are important, but we're here to learn. I hope that you learn and have fun in the class. So let's get started with actual astronomy. Look at that. I only took 22 minutes on the syllabus. I took 48 minutes on the syllabus this morning. So the kinds of things that astronomy is interested in. Galaxies. Galaxies are large collections of things. Now, there's a certain scaling in astronomy. Galaxies are really big. They're the biggest thing like this. But we have smaller versions. We have things that are called star clusters. Star clusters are kind of like galaxies within a galaxy. So we'll learn open clusters and globular clusters. Open clusters have less stars, globular clusters have more, and it makes a difference because of gravity and how they look. Then we have the solar system. Star systems are also similar to galaxies. So there's some scaling type things, but galaxies are some of the biggest things in the universe. The very biggest thing in the universe, if you go from galaxies up, you have clusters of galaxies. We live in a cluster that's called the local group. Very original naming there. The local group of galaxies, which now, if I remember right, somewhere around 30 galaxies in. And those galaxies are, the space in between galaxies is about 20 times the size of a galaxy. So you can think of it kind of like if all of us were in this room without the desks, and if we're just walking around blindfolded, we're going to hit each other, right? So that's what is happening in galaxies. Our Milky Way galaxy is a reasonably large galaxy. The Andromeda galaxy is another large galaxy. We are currently interacting with the Andromeda galaxy, and we expect sometime, millions of years from now, that our galaxies will collide. But we're also currently actively gobbling up a galaxy. There's the Sagittarius dwarf galaxy that is near the center of our galaxy that is being assimilated. That is, we're tearing it apart and taking stars and material from that galaxy and making it our own. One of the things that's really cool is the location of the sun is in the location where a tail, I think it's the tail of the Sagittarius dwarf galaxy, crosses the galactic plane. And so some of the neighbors around us could be from a different galaxy that are being assimilated to ours. We do know from the direction of our orbit that we are natives of the Milky Way galaxy. So you have those clusters of galaxies, and then you kind of have clusters of clusters. And the biggest thing is called the Sloan Great Wall, which is what looks like a big wall made of galaxy clusters. That's the biggest thing known in the universe. Really large. So now let's go down in size. Nebulae. A-E is pronounced E. And so that's the plural of nebula, which means cloud. This here is a very famous nebula. It's the Crab Nebula. And one of the things that's really cool about the Crab Nebula is that astronomers noted that the location of the Crab Nebula is the location where Chinese astronomers in 1065 found a guest star. That is, they said, here in the sky there was no star, and then suddenly one night there was a star. And it stayed for a few months and then faded away. And so astronomers just determined this is where that guest star was. And in fact, I can't see it in this picture, but somewhere in here, Yeah, I simply can't see it. Somewhere in here, there is a neutron star. And so our understanding today is this is the bones of a star that died. The star died and had what's called a supernova, where the entire star blows up and left behind this cloud of gas and the neutron star. Neutron stars, by the way, are not stars. Questions?
So, a nebula is pretty much like a dead star, I guess you could say, but like the remainings or whatever, or how would you
This one is. Nebula means cloud.
Okay.
And so a nebula is very generally a cloud of gas and dust. That cloud of gas and dust could be primordial. It could have been something that was created at the creation of the universe. Whether you believe in the Big Bang or you believe that God created the universe as it is today, I truly, well, I do care. I believe that God created the universe and all that's in it. But for the purposes of class, I am not going to concern myself with which way you believe. What I am going to concern myself with is that you understand the scientific interpretations and why we have them, so that you can say, this is what science says, this is what I believe, and have things sorted out. So you'll have to know what science says and how they understand it. Okay, so that said, the theory from science is that the Big Bang, you had all this energy, the universe expanded, things cooled. As it cooled, you had the energy forming matter, and you formed protons, and protons had collisions with other protons, and you formed eventually helium nuclei, and then it pretty much stopped. So virtually all primordial gas would be hydrogen or helium. And every measurement that's been made bears that out, that the universe is 91% hydrogen and about 8% helium. And so a nebula could be primordial gas left over from the Big Bang. Or it could be gas left over from a star that has died. And so this here is an example of a nebula from a star that's died. But there are plenty of other nebulae that are believed to be primordial. By the way, our sun is not a first generation star. That means it was not made from primordial gas, from a primordial nebula. And they determine that by looking at the elements. If you have elements that are more massive than helium in any reasonable quantity, then they say it's not primordial.
So how was our sun?
So this is part of what I want you to learn, right? The life cycle of the star. I'm not going to give you the whole 9 yards of it, but essentially there was a star lived, died, produced a nebula like this. And then you have a shock wave that goes to that nebula that causes the gas to condense again and form another star. And so that's the process for our sun. Was a star nearby had to die, and then a shock wave comes through and forms another star. Okay, then we get to planets. This here is Mars. This picture is focused on the Valles Mariner. I can never pronounce it right because there's marinara sauce. It's the Mariner Valley, or Mariner Valley, excuse me, Mariner. You know, the Seattle Mariners, everybody. So Marineris, yeah, Valles Marineris. And you can see that big gash on it. Now Mars is, of course, a near neighbor. It's not our nearest neighbor. Our nearest neighbor is Venus, but it's a near neighbor. And we have spent enormous amounts of money looking for water on Mars. I talked about that climate, other class. I talked about the climate orbiter that crashed. Why do we spend all this money looking for things about the climate, and specifically water on Mars?
Don't we want to try to get something on Mars? Like some, what is it, colony on Mars or something like that, and find out life is possible on Mars and that sort of thing?
I don't think that there's a lot of push for developing a colony on Mars. There is in the movies, by the way.
That's in the movie. I just had come across a couple little things that was discussed in the scientific community.
There are discussions about trying to terraform Mars to make it into a livable, habitable planet.
Because our planet is, we're thinking futuristic, our planet's dying.
Yeah, we keep making babies. We have to have a place to put them.
Overpopulation.
We're
Well,
to
there's
find
shade
out
and
like
orange
how
spaces.
water in our own planet came through like
Okay, to find how water came here. As I understand it, and this goes back to you guys are all so young, this occurred before you were born. But we had a vice president of the United States who was named Dan Quayle. Anybody heard of Dan Quayle? Elias. Julia, okay. So we have a few people who know who Dan Quayle is. Now, he was famous for saying stupid things. Sometimes it wasn't his fault. Example, he goes to some school, I swear it was in Iowa, and they're having a little spelling bee for the second graders. And the teacher has the cards with the words on it. And so Dan Quayle is going to be doing the spelling bee. So the teacher gives him the cards, and for one child, the word is potato. And the kid, unlike, Al Sharpton yesterday who spelled respect R-E-S-T-I-C-T. Read the regular tribute. Anyway, the little kid says it right. He says P-O-T-A-T-O. So close. Just missed the E at the end. And everybody just, makes fun of Dan Quayle. The thing is, his problem was he believed the teacher knew how to spell words. The teacher gave him a card that had potato misspelled. And he believed that the teacher wouldn't be wrong and overrode any knowledge he might have had. So that one wasn't his fault, really. He just didn't have confidence in himself. Other ones, like trip to Latin America, saying, now I really wish I had studied Latin harder when I was in school. Yeah, you don't speak Latin in Latin America, right, folks? Okay, so this one here. He was asked, specifically the question I'm talking about, why do we spend so much money trying to look for water on Mars? And Dan Quayle said, well, if we can find water, then that means there's oxygen. And if there's oxygen there, that means that we can breathe and we can live there. Yeah, that doesn't quite hold together. But it does come from, he must have had a briefing from somebody who knew what they were talking about, and Dan Quayle didn't understand it. Because the idea is, as we understand life, there's like 7 ingredients necessary for life. You have to have an energy source. You have to have water. You have to have, there's a list of things you need for life. And so if you have water and a heat source and, oxygen in the atmosphere, blah, 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 then we could live. And so they believe that perchance there could have been life on Mars before there was life on Earth. And that maybe life on Earth came from Mars. Maybe life developed separately somewhere else. They're looking for water because if there's no water, they know there is no life as we understand it. Now, we're humans, we're pretty limited. We only know life on Earth. But as we understand, there's no chance of life without water. So if we find water, there's a chance of life. And so that's a real motivating factor to try to find a laboratory somewhere out there off of Earth where life may have developed separately. Now, of course, I'm a creationist. I already said that, right? I don't believe that life evolved anywhere. But that doesn't mean I wouldn't say, yeah, go and look for it. So NASA does things, they really bend over backwards to try to make sure that we don't contaminate other places. So now we have landed spacecraft on Mars. And we now understand that there are certain things on Earth that can actually survive in outer space and could have been transferred to Mars. But when they had the Galileo probe orbiting Jupiter a few years back, it was about to die, and they intentionally crashed it into Jupiter because they wanted to make sure that the Galilean moons, Io, Europa, Callisto, Ganymede, I'm sure I said them in the wrong order, that they remained pristine, that we didn't have a spacecraft land there, because they wouldn't want the spacecraft to land there and to bring living organisms to one of those places, and then later we come looking for life, and hey, look, here's the life that we brought. And so they actually try very hard not to contaminate places that they could come look for life in the future. Okay, all that, planets, another thing that we study in astronomy. A lot of people, like coming into this class, just think astronomy, stars, and planets. And we'll learn a lot more than that. Then we have moons. So here is a 2-scale picture showing the Earth on the left and the Earth's moon on the right. A lot of space between them, right? But, you could count the number of Earth distances from the Earth to the moon. The moon is small. The moon is not smaller than all of the planets. It's larger, well, I believe it's larger than Mercury, way larger than Pluto, but Pluto's no longer a planet. Calm down there, Eli. We'll talk about Pluto and why he got demoted, of course. So we'll learn about planets and other things that orbit. And now we get to the first thing that's going to be on test number 1 for sure, the scientific method. So the scientific method is how we do things. And we start with scientific things. Everything is based on a reason. Nothing is, I feel this way. I think that it happened that way. Everything has to be based on a reason with an explanation. And you get those from reading other people's ideas. You might have heard a famous quote, I don't remember if it's Einstein or Newton, it's some great physicist who said that he's only achieved his heights because he's standing on the shoulders of those who came before him. Because if we always started from the ground up, we would never get very far. Now, of course, there's the other side of that coin. I often think, if I was stranded on a desert island, if, God forbid, all of humanity were to die except for me and my wife, how much could I rebuild? But I'm a physicist. As Sheldon Cooper would tell you, I have a working knowledge of everything important in the universe. Well, not so much, but a lot more than, I can make a compass, for instance. I got some things going for me. But you have to take the previous ideas and build from them. And then you test them. Scientific is really big on testing. Everybody knows experiments, but we're going to talk about why do we have those experiments? So we can test our ideas. If you go back to somebody like Aristotle, we'll learn the Aristotelian model for the universe, which has everything is orbiting around the sun, and you have these crystal spheres, and the planets are on the spheres. He had no tests to test this. He just simply said, this is a really beautiful model. And if it's really beautiful, it must be true. Whereas you get to Galileo Galilei, and Galileo said, we've got to test these things. We've got to know if they're true. We can't just say, it's beautiful, it must be true. So we test our ideas. And we invent explanations. We come up with hypotheses. Hypotheses is plural for hypothesis. That are based on scientific ideas. That is the work of people before us. That will explain what we're seeing and make predictions that we can test. Then we have experiments to test them. And, of course, part of the scientific process is reporting your results so other people can test them. Once again, you guys are way too young for this, but when I was in graduate school, which was not the Dark Ages, these two gentlemen, Pons and Fleischmann, were doing some research, and they came into work one day, and they found that their equipment had melted a hole through the concrete floor. And they said, of all things bright and beautiful, the only way that could have happened would be such enormous energy, we must have had a fusion event occur. And so instead of testing things out and making reports so other scientists could test their results, they called a press conference. That's going way outside of scientific protocols. They called a press conference and they said, we achieved cold fusion in our laboratory. That is, cold fusion is fusing hydrogen into helium, what's going on in the sun right now. Keep it up there, or keep it burning, whatever. We achieved that fusion, but in a cold environment. That's an environment where we didn't put in enormous amounts of energy. In the sun, we have fusion going on because there's so much gravitational energy compacting it. In a nuclear bomb, we have fusion that occurs, well, in a fusion bomb, a hydrogen bomb. The fusion occurs because you had a fission bomb that created so much energy, so hot. And they said we were able to do this without that heat. The world went crazy. I was in graduate school. I get up, I go to school, and everybody's running around like chickens with their heads cut off. Did you hear? Did you hear? Professors are all buying the materials that they said in the press conference they used. Problem was they were wrong. They hadn't done any testing. They hadn't given it to other people to do their independent testing. And so it gave scientists a real black eye because people were like, scientists don't know what they're talking about because they didn't follow the protocol. And your ideas have to withstand tests of criticism and modifications. Now let's think about modifications. The evolutionary theory. The evolutionary theory is a theory. What does it mean to be a theory? Okay, a hypothesis is like an educated guess, and you start with a hypothesis, but then what do you have to do with a hypothesis for it to advance the theory? Have to test it. A hypothesis that's been tested a lot and found to be correct is then considered theory. But a theory is never proven. Science never proves a theory correct. So many creationists will say, yeah, evolution is just a theory. It's just somebody's idea. They haven't proven it correct. Well, that's true. But it's also true that gravity is just a theory. And so if I take this pin and I drop it, unless I just drop my $100 stylus, if I take this pin and I drop it, gravity, the theory of gravity says it's going to fall, but it's just a theory. Well, of course it fell. Gravity is a very well-tested theory. It's one that no one doubts, but it's still not proven correct. Now with evolution then, people say, well, it's just a theory. It is just a theory, but it's a theory that's been tested a lot. Well, pieces of it have been tested. You will find plant creationists who say it's not a scientific theory because you can't test the whole thing. You can test this piece, you can test this piece, but you can't test if the whole thing works. You'll find other creationists that say, yeah, every time we point out a flaw with evolutionary theory, they just modify it. Well, yeah, you see where it says, and modifications? That's part of the scientific process. We never say we have the truth. We say we have the present truth. We have what we believe to be true, and I could be wrong. It could be that it will become more true in the future as we learn more about it. And so we learn more about it, we do experiments, we find, oh, it wasn't that way, it's this way, and we make a stronger theory by modifying it. So the modifications that are done to the theory of evolution do not make it weak. In the eyes of the scientists, that is the process of making a strong theory. Now, of course, I told you I don't believe in evolutionary theory, but you got to understand what it is and what science is before you can, discuss it intelligently. So here are the 4 steps that you have to have memorized for the first and final test. So step number 1, the scientific method. Now let me preface this. If you look up scientific method, you will find lots of different versions. They all have the same fundamental pieces, but you'll have different numbers and different orders, and some will skip a step, some will add a step. So this is what I require you to memorize because I think it's simple and covers the basis. So step 1, observe something interesting. You see something interesting that happens. And then being a scientist, a key to being a scientist is having a spirit of inquiry, wondering why did that happen? So step 2 is you develop a hypothesis, otherwise known as an educated guess, that will do 3 things. You have to remember to list these 3 things on the test. Number 1, explains why the observation occurred. Right? Your hypothesis is no use if it doesn't explain what it's supposed to explain. Number 2, it needs to be based on existing scientific ideas. Number 3, it has to make predictions that could be tested and it could fail. If you make a hypothesis that can't be tested and potentially could be proven incorrect, then it's not a scientific hypothesis. So your hypothesis has to have those 3 aspects to it. Okay, step 3, devise a test of one of the predictions of your hypothesis. Now note very importantly, this is not saying go back and test to see if your observation is actually what occurred. It's testing a prediction made by your hypothesis, and then you do the test. And the last step, If the hypothesis passes the test, that is if the prediction actually occurred, then you go back and you devise a different test that's going to test either the same prediction in a different way or test a different prediction. So if you pass the test, you're not done. You didn't say, yay, I proved it right. You can simply say, now let's go test a different thing. If it fails, on the other hand, then you go back and you have new information so that you can make the hypothesis better. You have now ruled out one idea so that you're going to narrow down the potential ideas and hopefully approach correct. Notice step 4 took you either back to step 3 or step 2. So there can't be a step 5. There would be no way to get there. The scientific process is never ending. You're never done. You just keep repeating, testing new and new ways. If we had an infinite amount of time and did an infinite number of tests, then we could say we proved something. But of course, infinity is unreachable. Okay, just a few more things before we let up for the day. A model, a theory, and a law. A model is a framework for understanding something. A model doesn't have to be correct. So I'll give you a really good astronomy model, which I don't have in the classroom. A celestial sphere. Now I talked about Aristotle believing that the planets were on these crystal spheres, and outside that crystal sphere was the celestial sphere. Celestial sphere is the sphere with the stars on it. And so Aristotle believed that there was this big sphere. Actually, I said around the sun earlier. It was around the Earth. I believe the Earth was the center. So he believed that there was this big sphere with all the stars on it going around the Earth. We know that to be incorrect today. And yet, I have a celestial sphere model back the other side of this wall, right here. In fact, I have a bunch of them. The celestial sphere model is still useful to us. The celestial sphere model, the model that all the stars are on the sphere, is useful to us because it helps us identify locations in the sky. Because the stars are so far away from us, the stars all appear to be moving together because as the Earth rotates, they appear stationary. And so, for all intents and purposes, we can locate something on the sphere by treating the stars as fixed objects on a physical sphere. But they're not really fixed objects on a physical sphere. So it's a model for helping us understand, but it's untrue. So models don't have to be true, but they're representations of something. I have, I think, a slide after this that shows atoms, so I'll talk about there. A theory is a tested hypothesis, something that's advanced to having a level of belief that, yeah, this really is true. It wasn't just a guess. And notice it has to be verified by multiple researchers. We don't have Richard Webb comes up with a hypothesis. Richard Webb tests it 10, 20 times, and now it's theory. Other people need to test because there might have been bias in my work or just plain sloppiness. Then we have the law. A law is generally concise language, so shorter, and often it has an equation you can use. So Newton's second law, that the sum of the forces is mass times acceleration. That's a law. It's been tested. It works very generally, and often we put it in that equation. So, planetary model. And this will be my last. Well, let's stop there because it's time for me to stop. All right, I'll see you all for lab tomorrow. I will, before lab tomorrow, have a homework assignment for you so you can get started on it. Yeah, sweet. Have a great day. Oh, one more thing in case you noticed or didn't notice. I record my lecture